Hello, welcome you all for course on Applied Biostatistics. In this video lecture, we'll be looking into some topics on exceptional statistical methods. In this video lecture, we'll be focusing on this particular part, that is logistic and nonlinear regression. Before we get into the topic, let us look into certain aspect of something called as discrete variable. In fact, it is related to the basic statistics, fundamental statistics, you can say. Can have different types of the variable. One of them is nominal variable. Now you can think of a nominal scale variable that has two categories. That means the levels of that are two. There are two outcomes, there are two representations of the nominal scale variable. In such a case, you call it as dichotomous variable. So there are two outcomes. You can think of something like gender, male or female. You can say outcome of one treatment, either the patient is surviving or death. Myocardial infarction also you can take as one of the characteristic. You can say yes, it happens, it doesn't happen. So patient dies because of MI, patient doesn't die because of MI. So either this or that, any two outcomes will be there. The outcomes will be only two. Such situations, such kind of nominal scale variable, you call it as dichotomous. Only there are two outcomes of it. Now if you talk about probabilities associated with that, so that proportion of the population, a fraction of that population which has got that event successful. Successful doesn't mean that it has to be good for you or bad for you. Successful in the sense the event whatever you are expecting should happen, that is success. Whether it is a failure or a success doesn't matter. So you can say that death is a success, the other way around, survival is the success. Both are true. Now let me say that you are utilizing this particular nominal scale variable for the case of gender, male and female. You are testing a population, is randomly you are checking the gender of the people, either male or female you will say, you come across. So all those proportion who are saying male may be P, that proportion is P, and the other one female you can say 1 minus P, or you can represent it as Q. So if you say that 50% is male, 50% female. Other way around, if you say 60% male, 40% female, that is 1 minus, the proportion is probability is 1 minus, as you are aware of it. Now this particular proportion is represented, the frequency of that is represented by binomial distribution or Bernoulli distribution. It's also called as Bernoulli distribution. So we have this learned this particular thing in the fundamentals first unit of this course, ABS 0.1 self-learning PDF. There you can go through this for more details. Remember that there is a binomial distribution associated with this particular probabilities. So my intention of taking this topic is to give you an idea what is a dichotomous variable. Right. Now let us move on to something called as contingency table. It is also called as cross tabulation or cross tabs. Now this is a table. It's a matrix with the rows and columns. Okay, R into contingency table. In general, it is called as. It is a frequency distribution of the variables. It has got R rows. You can see here R into C, rows into column. R into C stands for rows into columns. So R rows are there, C columns are there. So in the row wise, one particular variable is written, and in columns response is written. The usual way of representing is this way. This is the tabular format. Response variable is always shown in the columns here. Response 1, response 2, it may have multiple levels. A response can be having multiple levels. Explanatory variable, or you can call it as independent variable. The treatments that you are taking are represented in rows. So treatment may have level 1, 2, 3 or R different treatments. So the response variable is it can have multiple outcomes. Now let us look at the special case of dichotomous variable that we learned earlier. Now dichotomous variables have two outcomes. It is having always 2 into 2 contingency. R is equal to 2, C is equal to 2, 2 rows, 2 columns. Like so, all the variables associated here, explanatory variable or response variable, are having two outcomes. That's why we call it as R is equal to 2, C is equal to 2, and in general it is called as 2 into 2 contingency table. Now it is possible that both the variables, explanatory variable and response variable, are nominal, both are nominal, or both are ordinal ranked data, or one is nominal and other is ordinal. So this discrete variable only will be taking into consideration here. So these discrete variables you can write it in the form of 2 into 2 contingency table. Let me show you one simple example here. So I have exposure state, exposure to certain treatment. Let me say exposure is done, exposure is absent. So we that bar is usually represented as absent, and whenever you show it the independent variable in the rows, you will be mentioning control at the bottom, your treatment, actual treatment on the top. So independent variable always fall in the row wise here. Exposure state, this is independent variable. In terms of regression equations, we say y is a function of x. So x is the independent variable, y is the response outcome. So this is the response variable. Always response variable should be written on the for the columns. So outcome of the columns, you are doing a treatment. Now the disease state may be remaining as it is, it may be absent. So my whatever I want to predict here, my response variable will have two outcomes. Which response variable I want to do the test, that is very important. I want to identify certain thing. My assumption in this case is whether the disease state remains or vanishes. So I am testing for the remain. That means the disease state is not at all a risk factor still there. I'm checking for that. So event of my interest, most important thing is event of my interest. What I'm checking for, always the other one is 1 minus. I know that. So whatever I'm checking for, that will come in the first here. So that actual treatment and my event of interest should come first. You have to take care of this always when you write a contingency table, whether it is 2 into 2 or r into c contingency table. Now you have n number here, this one, n number of subject. Since it is a discrete variable, the total number will be fixed. So total number of population, what you sample, I can say we want to do the testing is n. It may be like 180, 190, some number. Now this 180 are distributed within this table. So what it shows is among those who are treated, e present, that is exposed means, let me say treated, those who are treated, n11, the first value, for them the disease is present, disease state is present. For these many numbers it may be absent. For example, this may be 20, this may be 50, some number. Add the two, 20 plus 50, total 70. This is the total row wise sum. Similarly, another set I may be having. So here it is absent and these numbers are present, same way for absent. In this case it is treatment is done, treatment not done. Treatment not done, this many numbers, maybe 70. Treatment is absent, other set of value. If I take 180, here it is something like 110 possibly. 70 plus 110, these two sum, if you add it, it should be n. Now same way here, if you add these two, these many patients are exhibiting disease state present, disease state is present for them. N11 plus N21 is equal to N dot 1. N12 plus N22 is equal to N dot 2. It is the column sum. So total how much disease state is present, total how much disease state is absent. This is belonging to E group, present this group N1, E bar absent for this group N2 dot. So total is N. So based on your experimental outcome, you can prepare the 2 into 2 contingency table. So for some time, let's leave it here. We'll require it later. Let us move on to something called nonlinear regression. Just brief introduction to nonlinear regression. We are not going too much detailed into this particular concept here. Now we have already learnt about linear regression and multiple linear regression in the previous chapter. There, for example, you have taken a calibration chart using Beer-Lambert's law. So we have seen that we can write the outcome, maybe something like concentration. We can relate it to the OD. So we have written B naught and B are the regression coefficients. Similarly, we can have the multiple linear regression. We have seen that in the case of factorial experiments where you have taken multiple variables, right? So you can write multiple regression equation for that. There are These are the only two types you can come across: linear regression, multiple linear regression. But when you come to the non-linear regression, there are many types of equation. and they are based on theoretical equation, empirical equation, semi-empirical equation. Theoretical equation means they are also called white box model. They are obtained as a result of principle from physics and chemistry. You have derived the equation. Just remember Michaelis-Menten equation. It is a non-linear equation. First order rate kinetics equation. This is a non-linear equation. So they have been derived from theoretical concepts. Another type is empirical equation. They are also known as black box model. In this case, in the case of empirical model, you are using the equation just because it fits well your output to the input. For example, monode growth kinetics. Monode growth kinetics, it is represented similar to the Michaelis-Menten kinetics, but this has nothing in relation with the growth curve. Growth curve in the sense the way the microbes grow. But this particular equation explains well the curve. Curve looks like Michaelis-Menten equation, that is sigmoidal curve. For that case, you can easily fit the data. So black box model or empirical equation doesn't consider any physicochemical principle. They just demonstrate how the graph looks like. Whereas semi-empirical model, you make use of both the feature. To some extent you will use the physicochemical principle, to some extent you use the empirical model. It's a combination of two. As an example, Colebrook equation. Like this, there are several nonlinear equations that you can come across. You may refer multiple reference materials. You get hundreds of different nonlinear regression equations. Now, the problem with this particular nonlinear equation is it is not like your linear equation. In linear equation, sum of squares, because of sum of squares, that is SS values what we calculate because of regression plus the natural variation error, that becomes equal to SSC, total sum of squares. There we calculate R square. R square is nothing but SSY divided by SST. So we generally take R square coefficient of determination as the say it is almost equal to 1, 0.9 to 1. We consider that is a good fit. But in the case of nonlinear regression, that is not the case. Just for example, you take one of the case. Say that you have an equation where you have multiple solution for y. Y is a function of x. I have not written here. Okay, y is, let me take some variable y versus x. Y is a function of x. For a given value of x, you may have multiple values of y. If you remember well how we calculate SSY, we take the fit and actual values. It's actual value and fit values. Now here you have one single fit value, or you can have multiple fit value. You can have single experimental value or multiple experimental values. So in general, what happens is this SSY plus SSC will not be equal to SST. Because of this reason, you cannot use R square as method, one of the result, one thing. Second one, least squares method what we use, which goes on this SSY concept. So we cannot use least squares method also to estimate the coefficients. Hence what we do is we use something called as maximum likelihood method. So maximum likelihood method, what it does is it identifies a particular output, whether it is it tries to fit with the iterative procedure. The output is fit to the input with the iterative procedure. Then it assumes a particular error, whether that error is met or not. Unless and until that error is minimized, it is iterating. So it revises the values of this beta. So the beta value what we have here, something like this, p or b or b naught or beta, these values are revised. So and new values of b naught and b1 are calculated for the nonlinear equation. Not these are the linear, but I'm talking about the nonlinear equation. And it is done until the overall error is reduced. There may be several different best nonlinear fit equation, all look similar. How do we identify which is best? For that reason, there is a method called as AIC. Beyond the scope of this syllabus, you can go through the additional materials available in the net. AIC, called as Akaike's information criterion. This is used for those nonlinear curve fits where maximum likelihood is used. This is useful to identify the scores. The AIC scores are used to identify whether a nonlinear fit is best among the several alternatives. So lower the AIC score, very low value of AIC score if you get, it is a better model. So that's about the nonlinear regression. Now let us look into one particular nonlinear regression, logistic regression. So logistic regression takes this way. So you have a dichotomous variable. You may have a dichotomous variable. It has two levels, and at least one explanatory variable is there, which may be continuous. Now what you get is the response outcome will be either 0 or 1. It happens, sorry, 1, it happens, it does not happen. So linear curve fit you may not be able to do. Any other nonlinear regression equation, if you try to fit, it may not fit exactly because of this condition. Another problem with the nonlinear regression is the value is always between 0 to 1. It is difficult to identify with any other nonlinear regressions. So y is equal to 0, y is equal to 1, in between that outcome will be there. So roughly the graph looks something like this. Maximum value is 1, minimum value is 0. It should be within that. So we can fit it use it to an equation called as logistic equation, which the basic model is this. Basic model is this in the sense you have only one parameter here for the explanatory variable, that is only one explanatory variable is present, x. X is the independent variable. So you have an equation exponential of alpha plus beta x divided by 1 plus exponential of alpha plus beta x. Alpha is a constant, beta is also a constant, beta is a parameter associated with the x. Alpha is a constant parameter, so there are two parameters here. So this is the least possible or simplest equation. So the value of pi of x, this pi of x is nothing but response y-axis value. This x is a continuous variable in the x-axis. Some books they refer p instead of pi. Now this is a probability value. It could be somewhere between 0 to 1, whether it is possible or not. That means if you have this particular value of x, whether the outcome is 0 or 1 or somewhere intermediate, so that you can identify using this equation. This is the most common or simplest equation. What is the complicated or multi next level equation? You can have one more variable, x1 and x2. Two variables are there, inputs variables are there, explainable variables, what we call independent variable. There may be two. We had multiple linear regression, right? Similar to that. In that case, how the equation looks like? Exponential of alpha plus beta 1 x1 plus beta 2 x2 divided by 1 plus exponential of alpha plus beta 1 x1 plus beta 2 x2. So that is slightly complicated. Similarly, you can extrapolate it further for n number of x values, that is explainable variables. This equation is also called as logit transformation. uh, Now here the probability value is calculated based on this particular outcome. Now this equation is obtained, equation in the sense alpha plus beta, two parameters what you have, they are calculated based on iterative process, that is maximum likelihood estimation method. So this is a non-linear equation. This is a non-linear equation fitting the dichotomous variables. So maximum likelihood method is used to identify the parameters alpha and beta. Look at that, they are all positive values here. The numerical value may be negative, but when you write the equation, the entire thing is positive. But the numerical value of alpha and beta could be negative or positive. What is very much important for us is, let me consider only one explainable variable here onwards, only one variable, x value only. If that is the case, what is the value of this beta? Whether it is 0, greater than 0 or less than 0. Now assume that it is equal to 0. When beta is equal to 0, the whole equation becomes a constant. That means outcome is independent of explainable variable. Understood, right? So the outcome is independent of the explainable variable. Explainable variable has no role in identifying the outcome. If beta is greater than 0, that means it is positive, beta is positive, then the probability of success outcome, the probability of success increases as x increases. In simple, this probability is directly proportional to x. The reverse way, beta is less than 0 means negative. If beta is negative, then probability of success decreases as x increases, means this probability is inversely proportional to x. So based on this beta, you can say something, that is probability is independent of x if beta is 0, probability increases with the x if beta is positive, probability decreases as x increases, inversely proportional if beta is negative. So three different cases you can think of. This is how you can evaluate that. Now, one of the important statistical tests we use to estimate we have calculated the beta naught. Whether it is statistically significant or not, we don't know. You can use Wald chi-square test. Usually this method, that is this particular process of maximum likelihood method, since it is iterative, you require computer software here. You manually, it is very difficult to calculate. Examination point of view or on paper solving point of view, you may not be able to solve this problem, but statistical analysis, once you get the equation, you can perform the statistical analysis. So the method what we use here is Wald chi-square test. Wald chi-square test tests very simple. It just tests whether null hypothesis beta, the null hypothesis for beta, whether this beta is 0 or not. That is the question. If beta is equal to 0, there is no association between explanatory variable and response variable. So it assumes that beta is equal to 0. You just have to disprove this. If you want to say that your equation is significant, your equation is statistically significant, if you need to prove it, you have to say that you have to reject the null hypothesis. What is the null hypothesis? There is no association between explanatory variable and response variable, phi of x and x. Alternative is the exact reverse of it. Test statistic is chi-square observed is equal to beta divided by sigma beta square. So what is this beta? It is the same beta which you get as the curve fit. This particular value beta, not the alpha. You are going to take beta. What is this? Yeah, beta. This is the parameter that you get across, that you get further from the equation. Sigma beta is nothing but standard error of estimate. Usually you obtain it as a part of the regression equation. When you perform a regression equation, you get a sigma beta. It is also called as standard error of estimate. Standard error of estimate. For alpha and beta, both you get it, this value. So the actual value divided by standard error, square it. You have to square it. You can see that it's chi-square, square it. So you get a calculated value. Compare it using a chi-square table. In the chi-square table, first you select alpha. Alpha could be our significance level 0.05. Usually we take 95% level. If you have to take it, then alpha is equal to 0.05. For 0.05, degrees of freedom equal to 1. Usually chi-square table, degrees of freedom 1 we take for Wald chi-square test here. So for this you check it, and as you know it, calculated value, if it is greater than critical value, then reject h naught. Reject h naught means there is a significant association. That's what we can conclude. This is Wald chi-square test. Here is a numerical. You can pause the video and go through uh, uh, the entire write-up and come back. You can pause the video here. All right. Now the summary of this problem is simple. They have done taken a different dosage of drug and taken some fixed number of mice. They have seen whether the toxic death toxic death is observed or not. Calculated the probability. They obtained this equation. This is the logistic equation they have got. Here x is nothing but dosage level. Pi of x is nothing but probability of death. This is the fit value. Once they have done the curve fitting to this equation, this is the fit value. For us, the question is test whether or not toxic death is associated with drug dosage. Means x and this beta and this equation, this whether this beta is significant or not. This is the question, whether x is associated with pi of x. That is the question. You just have to find out this beta is significant or not. For this, what we need to solve the problem, we need to use Wald square test. Wald chi-square test, you have to use it. You require beta. You can see that beta is equal to 0.488. Alpha is minus 6.381. It has no meaning in our test here. 0.488, this is required, and standard error of estimate is also provided, 0.0519. Let us use that. So let us set the null hypothesis. So the null hypothesis is, so there is no association between the drug dosage and toxic death. So alternate hypothesis, there is a significant association. So let us take alpha is equal to 0.05, calculate the chi-square statistic, 0.488 divided by 0.0519, square it, 88.1. Now if you refer the chi-square table for alpha is equal to 0.05 and degrees of freedom 1, the value of chi-square is 3.84. This is the critical value, and you can easily see that the calculated value is much above the critical value. So you can simply reject the null hypothesis. What do you say now? There exists significant association. There exists association. That is, you are accepting the alternative hypothesis. So that equation is valid. That's what you are going to prove it. Just go through this question. I'll pause the video. Alright, if you look at the equation here, the question is exactly similar to as previous. Blood pressure and cholesterol levels, two levels are given. So one is explanatory variable number 1, another is explanatory variable number 2. That means there are two explanatory variables. The outcome, it is given here, the endpoint of interest, reason for the death, coronary heart disease, CHD. This is the probability. And if you look at the equations here, exponential of minus alpha plus beta 1 x1 plus beta 2 x2, similarly in the denominator. The standard error of estimates for beta 1, standard error of estimate for beta 2, both are given. So you need to test whether there exists association between this x1 and pi, x2 and phi. So what you need to do is, as we have done earlier, but you have to test the two parameters, that is beta 1 and beta 2, separately, independently. You have to test it. So test 1, you can just go through this, you can pause the video and you can go through this. Alright, so here same method we use it, but in beta 1 we say that beta 1 is 0, that we compare for serum cholesterol level x1, pi of x versus x1, we compare it. Calculated value is 19.7, critical value 3.84. You say that x1 is significant since the calculated value is greater than critical value. Similarly, you will have to do it again for the x2. x2 is systolic blood pressure against pi of x. Here beta 2 is equal to 0, you will assume for the null hypothesis. Then you calculate the test statistic, beta 2 divided by standard error of estimate for the beta 2, that is 17.4. There you find that it is well above the critical value, so you are going to reject the null hypothesis. So this is how we are going to solve the problem. So just summarizing what you have seen what are dichotomous variables. We have found that it follows binomial distribution. Then we went through the contingency tables. You have seen what is R into C contingency table as well as 2 into 2 contingency tables. We have seen different types of the nonlinear equation such as Michaelis-Menten, Monod growth kinetics or Colebrook equation, and we also found that for nonlinear equation the sum of SSY and SSE not equal to SST, and we use maximum likelihood method to estimate the parameters. Then we have gone through the logistic equation, which uses the dichotomous variable as the response. So there are two outcomes, 0 or 1 for each individual values what we have seen. So simple equation also we have seen called as logit transformation. Then we have come across the test for hypothesis, that is the statistical test for hypothesis, Wald chi-square test. Thank you.